Welcome to 2022. Right before starting this video, those who wants to just see the tracker and it's working can skip to this part right here, but others can stay because this is a project I started last year. I made couple videos as well. Along the way I stumbled upon many barriers and overcame them. And those who watch some of those videos, they might find it insightful because I want to tell you what are the challenges I faced with respect to my initial plans and how I changed those plans. In other words, simplified them, made a working prototype. So that one was Mark 1. The Mark 2 is already finished and I am currently working on a Mark 3. But in this video, I'm going to only show you the Mark 1 and a little glimpse of the Mark 2. Let's get started, shall we? So if you chose this path, then you already know that I was planning to design a star tracker from the scratch, and that's why I initially planned on designing some sort of gearbox. That's why I chose 2 gears for it. But very soon that turned into a disaster. I mean, not a disaster, but as I didn't have proper tools to make a gearbox, I thought of eliminating that idea. So that left out with only one option, that is a Barndoor design. Initially I was not planning on going through this Barndoor path because it is not at all portable, and as I live in a city, I mean, it's pretty light polluted sky and everything, so to capture some good images of the sky I need to travel to a village or some sort anyway, so why not make it portable? But it didn't work out because it is complex. So I started making Barndoor design, or rather Barndoor tracker, and it's pretty common in the DIY star tracking. So the basic design is like 2 plates, a hinge here, so it will open like this, and this opening should be at the rate at which our earth is spinning. So that's how we track the sky. So our center of rotation will be the northern hemisphere. It is the Polaris around which everything rotates. This is the main concept. Anybody can make a Barndoor tracker, but that's not me. You already know. I was going to make the most advanced Barndoor tracker to ever existed. Anyway, I started designing this Barndoor tracker. This is all the calculations you need. So basically there is a website where you can do this easily. So you have to choose what RPM you are going to use
and the pitch of the threaded rod.
And according to that, it's going to tell you how much length of the plank you need to use. So I was initially planning for 1 RPM drive because it's pretty easy to achieve. But as I saw the plank's length is pretty large, and again, as I told you, I want portability, I chose a 0.5 RPM drive. So my plank length came out to this. I'll leave all these links in the description down below.
And for the driving mechanism,
I still didn't eliminate my worm gear because that's the most efficient way to reduce speed, as the sidereal rate is pretty low. As I already told in one of my previous videos, a worm gear literally have 1 tooth. So whatever gear you attach to it, for every 1 rotation of the worm gear, that other gear you attach to it is traveling only 1 tooth. So it's the most efficient way to reduce speed. So see, this is what I'm planning to do. It's like fixing this motor assembly with the upper joint, because it will come down, and with that my motor will move as well. But this thing is complicated as f. As you can see, I've designed this contraption using a copper pipe, and as you can see, if I like screw it there, then I can attach it with the motor assembly right here, and like that it will be attached with the upper plank. So whenever the upper part will move, the motor assembly will move with that. You have to design another for other side so that the whole thing keeps on balancing. And for this part right here, I've attached this copper pipe to make it balanced so that it doesn't release this gear right here. Otherwise the whole thing will fail. I don't quite know how well this will work though. Things are complicated as nowadays. Let's continue working. There's only one way to find out. Oh,
A few moments later.
you can see I've fixed the motor assembly with the upper plank. And now I will test it whether it works or not. But as you saw, the construction is pretty complex. It has a lot of flex, and that's why eventually I had to scrap this idea as well, because as you can see here, I put my camera on top of the tracker, and you can see this motion is not smooth. That is because my construction has a lot of flex in it, and it flexes at every rotation of the threaded rod, so pretty much useless. The sky doesn't jitters in motion, it is smooth. To track it consistently, we also need to design a proper smooth tracker. So that's why I have to eliminate that plan as well. And that was a huge hit. As I already told you before, as I gone with a 0.5 RPM drive, eliminating this worm gear is a huge hit. But I needed to do so, because to cut complexity, we need to eliminate things. Or in other words,
the best part is no part. The best process is no process. It weighs nothing, costs nothing. Undesigning is the best thing. Just delete it.
In my case, I just did that. So now, as I eliminated everything, I will just attach my stepper motor to a threaded rod directly. So even though I was planning on using 1/4 microstepping, that didn't work out, and I had to go with half stepping, because the torque at 1/4 microstepping, as I've already discussed with you before, a microstepping video, you can check the link in the cards above. As you can see, we are energizing both the coils in one step. In the next step, we are just energizing one coil. That means there will be variation between the power of those two steps. The torque reduces, and it cannot drive the tracker properly with my camera on top. So I need to go with half stepping, and that increased the torque a little bit, but at 0.5 RPM and half stepping, I had 96 steps per revolution and have around 1.25 seconds gap between the steps. And as you can see in this app, it's so I will just pause the video right here and I will show you what this app actually does. So as you can see, I can set my camera up and everything, so it will take the crop, my sensor size and everything in mind, and will tell me what's the max amount of exposure time I can set it up, so that my stars will not appear as in the sky. Or in other words, we cannot go above this number. If we go above this number, then the stars will appear as trails. So this number, as you can see, aperture, this is the opening of the lens, and we need to set this as little as possible. I mean, this number f-stop, we call it f-stops. So lower the number, the bigger is the aperture. So to capture more light, we need to lower this number as much as possible. Now my lens allows at 300 millimeters, it allows f6.3. So I'll select this, and you can see I have a max amount of exposure time of 0.64 seconds. In other words, I cannot have my camera stationary higher than this time. So in this case it's 0.64 seconds, and in my case with half stepping I have 1.25 seconds. So that's literally double, and that means my stars will appear as trails and not spots anymore. So to counter that, I have to reduce the focal length. Even at 200 millimeters, you can see it says 0.9 seconds. So I'll be pretty much limited to around 70 millimeters, or maybe even 100 millimeters. Obviously, the aperture will change. At 70 millimeters, the lowest it supports is f4.5, so I can pretty much capture anything at this aperture at 70 millimeters, as you can see. So my dream of capturing smooth nebula at 300 millimeters will not happen. I have no options. And while making the design, I could visualize, I could eyeball that the mount is not going to support a larger lens, because how finicky that is. It's literally janky. So I lost hope of capturing at higher focal lengths. So for smaller lenses, like suppose 50mm, it's still gonna do okay. So that's why I'll stay with those half stepping. After all, it was a pathfinder. So right after elimination of the gear and attaching the motor directly to the shaft, the threaded rod, I did this exact same experiment, putting my camera on top, put it on time-lapse and run the tracker. And you can immediately see how smooth it is now. This is what we needed to achieve. Now comes the tangent error part. There are a couple types of Barndoor trackers do exist. The main variation amongst them is the driving mechanism. And in my case, I had a straight rod, and with time, when the tracker is running, the geometry changes and there is something called tangent error. If you're using a curved rod mechanism, this tangent error can be minimized, or rather eliminated. But in my case, I had a tangent error, and for that I needed to use a corrective piece. So I did it like this as well, just for insights. I'll leave an instructable link in the description down below from which I followed this design. And though I didn't encounter any tangent error with or without this corrective cam, probably because my total tracking time is short, as my threaded rod is short. But if someone tries to make this with a bigger threaded rod, probably tangent error will be a factor. So that can be eliminated. For the control electronics part, from the very beginning I was using ESP01 Wi-Fi module and controlling it using a RemoteXY UI in my phone. So the code and everything is linked down in the description down below. I created a great Git repository and it is archived right now as the project was officially ended. The Mark 1 was a great pathfinder, and that helped me to design my second prototype, which I will show you a little glimpse in the demonstration. Any one of you can download it and make it yours. So to write up with the testing, some more delivery designs and things. How am I gonna supply power to my tracker outdoors? I chose some lithium-ion cells laying around and designed a protection circuit, plugged it with that. At that point we were pretty much done. Here is a little time lapse of me finishing the version 1 prototype. Yo, what is this guy doing over here? This is temporary shit at its fullest. Look at that. Somehow I managed to fit everything together. But for the fan, I had to do some crazy architecture shit. Because the fan is so large, it's nice to fit in. And here is a demo. So This is the final design I came up with. As you can see, the hair is pretty wonky. You see that? That's because of my tripod. It's pretty cheap. Now here's the stepper motor I'm using. It's the same 48 steps per revolution, and I am using it in half stepping mode. This is a fan. As I was using an improper driver to drive it, it heats up quite a bit. So to cool it, this is a fan right here. These are all stopper switches, contacts basically. So whenever it comes up, it automatically stops using that stopper. We have one more stopper at the bottom for the same upper stopper. Anyway, this is for the stop. This is for the top stopper, and this is for the bottom stopper. And this is the thing I was using to correct the tangent error. You see how shiny that is? I attached this for a polar scope sort of thing, but it doesn't work anyway, so I don't use it. I will show you how I polar align it. It's currently polar aligned. For a rough alignment, I attached this compass over here. You see? It's pointing towards north. Now coming to the main electronics part, I have this battery compartment where we attach 3 18650 cells. So I will have 12.6 volt fully charged. And inside of this basically I have my homemade overcurrent protection circuit. And there I have the battery indicator. And these are all those charging modules. It's pretty janky, but it works out, and it is good for a proof of concept, Then I have here my main electronics. I have the Arduino attached over here. Currently it's not there. And I have this ESP01 module, which I use for Wi-Fi, which I used to connect to Wi-Fi to connect the whole thing basically. And down there I also have that motor driver, which is not suitable for driving stepper motors, but still I'm using it. And I have some temperature probes attached for this motor driver and this ESP01, and I monitor those temperatures. And whenever they increases, because this ESP heats up quite a bit, I run this fan through this driver right here. This is a speed controlling driver. I used a MOSFET and I'm using the Arduino to control the speed of the fan basically. So that's it. But what's the problem, you may ask? Well, as I'm using 96 steps per revolution, it's quite low. And as I show you before in my app, it cannot take images at certain focal length. Currently this lens is 50 millimeters and it's quite good at this. I'll show you some examples later on. But when I use, suppose this bigger lens, this is 300 millimeters, and go up to 300 millimeters basically, it doesn't work. And also this whole thing is quite cheap, as you can see. Also the motor is not that powerful, so for bigger and heavier lenses it cannot drive properly. Even I broke the tripod head and have to replace this using these janky washers. That's why I'm working on a much more improved version with the NEMA 17 stepper motor and this whole drive bolt, these heavier clanks, and a whole new level of proper stepper drivers basically. And also I bought a couple things like a better tripod, a better ball head. You see, me versus the guy who is just a friend. That video will be coming soon. So now let me show you how I polar align this thing. So see, the initial level of polar alignment is done using this compass. It's a manual mechanical compass. So once this polar alignment is done, it is pretty coarse polar alignment. And then what I do like this and use an app. So this app is called Polar Scope Align Pro. This is not a free app, but what it does is pretty nice. That's why I bought it. So let me show you how this works. So there is a feature called daylight mode, and see, I can just adjust the polar alignment using this crosshair right here. So there it is. I have to just keep on adjusting this until it finds the crosshair meets the center basically. It's pretty useful to, it's pretty easy to do. And after the whole head broke off, I can also adjust this altitude. See? It's pretty handy, isn't it? And guess what? This is pretty accurate also. Let me show you some pictures I captured using this. So I'm back in my computer and I will show you the different images I am able to capture with my tracker. So this is the one session I only did for testing basically, and I'll show you what I'm able to capture. So see, these are the images I am able to capture of the Orion. But sadly, Orion was not at the very top, so this is my thumb rule. I capture these images when they are at the very top so that I can avoid as much light pollution as possible. So at this time it was December and it was not quite at the top. I mean, it could be in the top if I would shoot them like 1 AM in the night, which I didn't did. I shoot this I don't know, maybe at 9 PM or something. So they were not quite in the top, but I just did it because I wanted to test my tracker. So as you can see right here, I took this at aperture f4, 15 seconds at ISO 200. So these are all settings you don't have to worry about. The only thing you have to worry about is this 15 seconds. So as you can see, I still have some trails, so let's select this one and see, the stars are pretty round, and look at that. This is how you can capture, I mean, this is how much you can capture with this particular tracker with proper polar alignment. And again, I was using only my smartphone to polar align. That was not at all a precise alignment, and it is forgiving at suppose 50 millimeters. 15 seconds exposures are possible. So this was with this particular tracker which I showed you. This is the Mark 1. But about a month or 2 months later, I was working on my Mark 2 prototype, and I also captured the same constellation, I mean that is the Orion, and I'll show you how it looks. So you have to keep in mind the amount of seconds, I mean the exposure time really matters what you capture. I captured 15 seconds, that's pretty good. But if you can do that like 30 seconds exposures at larger apertures like f2.8 for example, it will be incredible. And see, this is what I captured a month later, and these are 8 seconds exposures, and this time the aperture I kept at 2.8 because I was facing some difficulties getting more time, I mean more exposure time, because this, remember, this is my Mark II prototype. which is currently finished, but at that time it was at very preliminary stage. So I'm just showing you, for example, that with the Mark 1 I captured 15 seconds exposures, but that was pretty light polluted, and this time I captured this when Orion is just at my top right there, call it zenith. So I avoided much light pollution. I mean, I avoided a much more amount of light pollution, and see what I'm able to capture, and I will show you the stacked data. So this time also I'm able to capture around 100 of these images, and when I stack them, see, this is the amount of details I'm able to capture. Look at the Orion Nebula. Isn't it incredible? I mean, there is a lot of noise. And as you can see, these noise patterns, these are called walking noise. And look at all these beautiful starlights with these star colors. This is possible from a bottle 7-8 sort of sky. Now I'll show you what is that scale. See, this is my sky quality with the exact same constellation which I captured, Orion. Now my sky quality is like this, 7-8, and in between of those. Now suppose what is possible from bottle 4 then? Bottle 4 is pretty easy to get. You can even see rosette right there. Now I push this image to much further, and you will see how it looks. See, the core is pretty blown right here, so I not particularly like this, but I wanted to see how much I can push it. So you can still see a little bit of the lower part of Orion Nebula, and a little bit Running Man as well, and also you can see the Flame Nebula. Look at this. Remember, this is the same image which I showed you. This one. Now, why I'm showing this to you, you can do much better than this. This is just a test shot with my Mark II prototype, which I was not able to capture using the Mark I because of the time basically. But I wanted to improve. You can do a lot better with this star tracker if you get proper polar alignment, maybe if you live in a darker sky location. Even bottle 4, I will show you one image right now which I am able to capture using my Mark II prototype, and at 200 millimeters in a dark sky location. See, this is what you can capture as well. Now this is captured at 200 millimeters from a bottle 4 sky with my Mark II prototype. This is not possible with the Mark I, as I showed you why. Because the motor I was using, the tripod I was using, the tracker is pretty finicky and it cannot carry that much load, and also the motor is not that capable. Now for this I have captured around 320 images at 200 millimeters and 5 seconds exposures, because I cannot go higher than that because it was the star cell trailing. I mean, in this case also the star cell, you can see some awkward star shapes right there. That is because of my lens, as well as I don't know why this is for though. It's probably because of my lens and field drift. That I'm not going to detail, but this is also a test shot. I visited one bottle 4 location, and that's why I took my Mark II prototype with me to test it basically, and this is what I'm able to capture. Look at it. This is what I'm able to achieve. Look at that. It's still a lot grainy for my liking, but you can see the lower part of Orion, and this Running Man nebula. Isn't it incredible? I mean, this is I'm getting from a DIY thing, isn't it? And as you can see, the stars are not very round, and that's why this is solely depending. This is solely because of the polar alignment. The more higher the focal length you go, it's incredibly hard to polar align everything. So it was a great project and a great learning opportunity, and as of shooting this video, I already made my second prototype and officially sort of ended it and started working on a third one. It will also support auto guiding. If you don't know what auto guiding is, Google search. All those videos are coming soon, I guess. Anyway, hope you have enjoyed. Like, share and subscribe. This was Manar. You are watching Outta Syllabus, and for today I'm signing off. Peace out.